All right, our next presentation is looking at keeping the lights on, how AI enables the energy systems of the future, to be delivered by the Chief Data and Analytics Officer at Siemens Energy. As we know, a huge drag on energy, AI systems being deployed all around the world, but it can be a force for good as well. She's an expert in leveraging data and AI to drive value and solve complex business challenges, and she's passionate about driving data and AI transformations. Please put your hands together for Micheline Casey, SVP and Chief Data Analytics Officer at Siemens Energy.
Hello and good afternoon. I was a small child growing up in Middletown, Pennsylvania, when the principal came into the classroom the morning of March 28, 1979, and said we needed to leave school quickly. A few hours later, sirens started going off, and my family was forced to evacuate. It's because we live next to the 3 Mile Island nuclear power plant near Harrisburg, Pennsylvania. 3 Mile Island is known as the site of the worst nuclear accident in US history, and it had just experienced a partial meltdown. There was a combination of problems that were the cause for this, including design-related issues and worker problems. But the instruments at the time provided very inadequate information to those workers, and the systems were analog, providing very limited data. For example, there was no way to know that the release valve that they thought was closed was actually open, releasing much-needed cooling water. And there was no sensors to know that the reactor core, which should have been covered in water, was not. This was a long time ago, but the experience still sits with me as I think about how much energy production has changed since then, and with nuclear coming back into the news so much to power AI models. Once centralized, analog, and powered by relatively stable fuel sources, it was relatively easy to forecast and manage power consumption. But today, things are much more complex. Hi, I'm Micheline Casey. I'm with Siemens Energy, and we're a leading provider in the supply side of energy management systems. Our products and solutions are used to power over 1/6 of global energy production, and we're a leader in the digital transformation of energy management systems. Today, I'm going to discuss why artificial intelligence, while consuming so much energy, is also crucial for the future of energy management. Today's energy systems and grids face enormous pressures with a few factors in particular that are to blame. First, the demand for energy is increasing at the fastest pace in years. Global energy consumption and electricity consumption is surging, increasing at its fastest rates, fueled by robust economic growth, the intensity of more and more heat waves, and continued electrification worldwide. And as all of you know, the demand for data to run data centers and AI models is now increasing by 160% forecast through 2030, with AI alone driving at least 20% of that demand. Now, to be honest, I'm not sure anymore, when I pulled these statistics 3 weeks ago, that they're still valid, because the numbers are changing so fast. But as everyone in this room knows, the energy used by an AI query is at least 30 times that of a traditional Google search. Secondly, while it is absolutely critical that we move to renewables, renewables bring additional complexity to the management of the grids. Wind and solar are intermittent, meaning we can't predict when the wind's going to stop blowing and when the sun's going to go behind clouds for long periods of time, which makes them less reliable for energy production. Additionally, consumers and businesses are now adopting smart energy devices at increasing rates, which is great, and they're also getting the opportunity to sell data back to the grid. I don't know if you've seen this, but I used to work for Ford, and our Ford F-150 trucks are used now to power homes in hurricane outages. And it's an amazing technology feat, but it also injects a huge amount of complexity because the grids were not originally designed for a massive addition of connection points added every day. Which leads to perhaps the biggest challenge, which is that the energy infrastructure, the grids, are largely outdated and analog. As countries push to meet their global climate targets, many face backlogs because they simply cannot plug those projects into the existing grids. The UK alone has almost 400 gigawatts of power projects that cannot be plugged in, with delays of up to 15 years. And the infrastructure is old. In the United States, at least 70% of transmission lines are over 25 years old. And Europe faces similar challenges, with about 40% of its infrastructure nearing end of life. These systems were largely designed and built and implemented in the 1960s and 70s when man first walked on the moon. In order to meet climate goal targets, we need to add or replace 80 million kilometers of power lines by 2040. That's the entire length of today's grid that needs to be done in the next 15 years. The current systems are simply sagging under the requirements that the new systems actually need, which increases the risk of major power outages, the frequency and duration of those outages, as well as increased cybersecurity attacks. So then what does the future of energy systems hold? Well, we do know what it needs. The future demands modern digital grids, which are flexible, responsive, and can manage multi-directional energy flows fluctuating throughout the day and evening. In the future, they will largely be automated because the sheer volume of information, the speed of decision timing, especially with the injection of renewables, and variable complexity means that artificial intelligence-powered forecasting decisions and operations are crucial. Now, AI will not solve every problem facing the grids and tomorrow's energy operations, but AI and digital technologies do hold, along with deep domain expertise, tremendous potential to enable the evolution and potential revolution for the future of energy. Systems which can optimize energy management in real time, enable configurable changes based on business needs, autonomously manage operations, and perhaps self-heal and self-diagnose, and to improve the overall reliability and security of grids. Now let's take a look. I'm wildly optimistic at potentially what 2040 looks like in an automated, unmanned, and configurable world. And I think the best way to do that is to compare what things sort of look like today. So many of you flew across the Atlantic and saw many offshore wind farms out in the North Sea. I would guess many of you saw those. Today, when something happens out there, you need to take a ship or a helicopter. You need to take a crew of people, and hopefully you have brought the right equipment needed to fix the problem, whether it's on the blade or another piece of equipment. As you can imagine, this is extremely time-consuming. It is very expensive, and being out in the water poses a host of safety-related issues. So what could a future look like if this whole wind farm was operating autonomously and could either self-heal or predict close enough when something's about to go down that we can send an over-the-air update to it and fix the problem, similar to how we do a Tesla or our mobile device? And what if we could also bring the CEO or CFO into that control room, perhaps with their mobile device? By 2040, there'll probably be something else, so that they can adjust as macro or market conditions change, so that they can optimize whatever key factors are important to them in the moment, whether it is driving more energy production, rebalancing carbon emissions, or adjusting to energy price fluctuations. So what we're talking about is intelligent production operations, mostly running autonomously, allowing seamless real-time adjustments driven by business goals, powered by an AI operating system. Now, to be honest, getting there will take some time. Not only to develop the component pieces, but to get the physics of energy right, because that is critically important. But we are building many of those pieces today, and let's take a look at some examples. For those of you who have never seen, we all know what happens when you turn the lights on, but these are some of the ways the power actually gets generated and comes into your home or business. Let's talk about autonomous operations. Similar to autonomous vehicles, and we just heard a little bit about that, there are various levels of autonomous industrial operations. But achieving full autonomy can only happen by understanding the individual components that sit on these very complex pieces of machinery and equipment, and understanding the related physics. Physics such as gas flows, and fluid flows, and material science, and chemistry. Once we're able to understand the components and how they work together, then we're able to understand how they connect together as a solution, and then from solution to grid, and potentially grid to grid, particularly as grids are getting more interconnected across regions and geographies. Using digital twin technology, combined with artificial intelligence and high-performance compute, this creates significant opportunities for us to be able to model this level of complexity. During the design phase of these types of solutions, we create virtual models of the physical components and then simulate and optimize how they'll work together in real life in production. When we get them into production out in the field, we have them connected with smart sensors. And along with cloud software and edge analytics, we then are able, along with our customers, to optimize operations. Our machine learning models are able to take real-time data, combine it with external data, such as weather, energy price fluctuations, et cetera, to be able to monitor and manage productions. Our algorithms can also perform today remote diagnostics and predictive maintenance, which supports our customers in maximizing efficiency and uptime for their assets. Now, moving on to grids, which is really the most critical piece of infrastructure. We are pioneering the use of cutting-edge PINs, physics-informed neural networks, to be able to model these complex multi-physics systems. Again, we're talking about the intertwining of gases and fluids and materials. These are extremely complex systems. PIN technology, and I think we just heard a little bit about NVIDIA, allows us to blend the real physics constraints with traditional machine learning to be able to predict certain types of equipment failures before they occur, which traditionally would have been quite difficult. For example, hotspot identification on a bushing piece of equipment. We use thermal models to be able to detect real-time overload and heat transfers between these sort of grid components, and we're able to send alerts to the operations managers. This, for us, has resulted in model response time speed up of over 40,000% increase at the same level of precision, if not better. This has been game-changing for our data scientists as well as our engineers and our customers. With grids as well, we're also using slightly more traditional technologies, drones, robotics, paired with computer vision and image analytics, to do remote aerial examination of transmission lines, as well as other grid components such as transformers. This supports our customers with in-field maintenance and repairs, because as you can imagine, there are hundreds and thousands of transmission lines that they would have to manually inspect. Using these types of technologies paired with AI, it really allows our customers to hone in on very specific areas so that they can save time, they can save labor costs, and avoid downtime in those pieces of equipment. Now, earlier I spoke about the speed of decision cycles, especially when these energy systems are becoming more complex and more renewables are coming into the systems because there are simply just more fluctuations and decisions that need to be made in microseconds. It's been amazing to our researchers and key scientists to use artificial intelligence and PIN technology on high-performance compute to increase the speed and precision of complex models, which previously would have taken hours, sometimes days. For example, a traditional computational fluids dynamic model, from a simulation perspective, usually takes about 26 hours to output a 10-hour prediction window. Using graph neural networks now, it takes about 2 seconds. It's these types of magnitudes and performance that gives us the confidence in what will be possible for autonomous and stable operations in the future. One of the most impactful ways, though, that AI has been improving the energy market is simply predicting supply and demand, especially as we're seeing the speed of electricity consumption with AI models increasing. Developing this greater understanding of when power is available can be extremely complicated, especially with renewables, because again, we don't know when the wind is going to stop blowing or when the sun's going to come back out. And machine learning and AI is really helpful for being able to match the rise and fall of supply with load dispatch, which can change very, very quickly. Now, something probably dear to all of our hearts is reducing carbon emissions. For several years now, we've been able to use AI systems to monitor carbon emissions output and environmental impact off of our equipment in real time, which helps our customers support their compliance with their own sustainability targets, as well as analyze opportunities for improvement in their energy operations. AI enables our customers to both reduce emissions while improving and increasing plant efficiency and reaching the desired performances that they need across their energy operations, including, again, that flexibility that they need for dispatchable power when we've got a lot of fluctuation with renewables. Internally, we're also using artificial intelligence to monitor our own carbon output as well as improve our own manufacturing operations. So we're using multiple types of AI to do this. We're using digital twin technology, we're using computer vision, we use acoustics monitoring, optimization techniques, and Gen AI to support our manufacturing processes. For example, in the manufacturing of the world's most powerful gas turbines from our factories. AI helps us make our own improvements in production quality and optimize the use of manufacturing materials so we can reduce waste, which helps us support our own sustainability targets. Again, we're still at the beginning of this, but I think some of these use cases show how AI and digital technologies can be used across the value chain to create, to manufacture, to operate, and to service and fix energy generation solutions. So again, while I was wildly optimistic about 2040, we are making large strides, and artificial intelligence in particular is helping us get there faster. And as AI technology continues to evolve, we continue to innovate along with our customers to define new ways of using it and working with it for the future of energy system digitalization. And now coming back full circle, we're seeing these becoming intertwined. And I know we talked about this at least once, maybe twice over the last couple of days. But just a few weeks ago, Microsoft announced a major deal with TMI, 3 Mile Island, and the owners of 3 Mile Island to reopen the nuclear power plant, the same one that forced me to evacuate when I was a child. This 20-year agreement allows Microsoft to purchase the entire amount of nuclear energy to use for local and regional data centers and AI models. This is enough energy to power 800,000 homes for 20 years. For me, at least, the symbolism of this is enormous, but it also follows the trends that we're seeing and have talked about in the last 2 days of the big 5 tech firms continuing to build or acquire large amounts of renewables or clean energy to continue to power these very energy-hungry AI models and systems. But fortunately now, AI can also be used to develop innovative solutions on how to reduce the energy consumptions of those models, as well as to prevent another incident like 1979. The energy landscape is evolving very rapidly, and while the challenges are immense, we believe the solutions, a modern grid, renewables, and smart technologies are well within reach. As an industry, we're still within the early days of exploring how AI can unlock the full potential of future technology landscape. But what's really key is that AI's ability to manage the complexities that the modern energy landscape brings is a testament to its actual potential to ensure a more stable, efficient, reliable, and decarbonized power grid. Thank you so much, and I'm happy to take any questions now.
Thanks, Micheline. Wow, sobering talk. I guess while we're waiting for people to raise their hands in the audience for questions, please raise your hand. We have, actually, would you go straight to this gentleman
I
over
want to
here?
ask if anybody else was there besides me. Am I the only one who was there?
Who was where? At 3 Mile Island?
When it melted down? Yeah, I guess I was. Okay.
Just you. Yes.
I've asked this question of other guests previously, but
Sorry, can you just... yeah.
sorry, I've asked this question of other guests in other panels previously, but I want to ask it to you specifically.
We need...
sorry,
excuse me. We need the monitor at the front, please.
Robert Heinlein was a science fiction officer in the early 60s and 70s, and he wrote a book in where he talked about laws of computing for AI and computers, where he said, law number 1, computers will do no harm to a human. Law number 2, a computer shall not harm another computer unless it's trying to violate law number 1. And there was a third law, I forget what it is. But essentially, people at Siemens level who are working with AI systems, y'all need to put stuff in your computers to protect the human side of the world.
Yeah.
And, go ahead.
Thank you so much. No, I think the underlying point that you're bringing, ethics and governance in AI, even in energy systems, is something that's quite important. I think I was chatting with someone yesterday. If we think about this sort of future, and all of a sudden the machines need more electricity, are there now underserved populations that the algorithms decide to cut off from electricity in order to power those machines? It's something that we need to continue to explore and discuss, but thank you so much for raising it.
Do we have another question from the audience? Yes, over here. How are you an optimist?
I do glow in the dark, by the way.
Oh, man.
Good day, thank you. I'm a journalist from Latin America, and so my question, one of the biggest problems that we have, at least in Central America, which is where I'm from, is power outages because of problems with the transformers and these sorts, and the substations, et cetera.
Yeah.
So I just was wondering if you could speak a little bit more as to where we are with this AI technology, timetable or technology until we are able to deploy these solutions so that we can prevent these things from happening and thus prevent power outages, which in some of our regions are daily. So
Yeah, thank you for the question. And I think Latin America is not the only region, right, that experiences major outages. And there's many underserved populations. So I think part of it is the technology, right, and getting the physics correct. But there's also the really critical investments needed by countries to actually upgrade their grids, right? And we're thankfully doing many major deals with countries around the world now to exactly do that upgrade. I talked about the 80 million kilometers that need to be upgraded. I don't know specifically about what that looks like and means right now for Latin America, but we can talk about that perhaps offline. Thank you.
I mean, look, you're on stage, so I got to ask you, is there a danger that we're prioritizing the needs of data centers over, communities that are seeing blackouts?
I think there is the potential for us as a society to understand how we want to invest our monies and make sure that things are equitable.
Yeah, I think it's something that voting power certainly and having conversations certainly can help us in that direction. I think that's it. Very quickly, there's a lady at the back. Can we get the microphone to her, please? Yep, great, thank you. Speak up if you don't mind, that'd be great.
Hi, my name's Kat. I'm a software engineer, and this is something I'm super passionate about as well. I know you mentioned not being able to predict the wind or the sun, like solar power, renewable energy. I'm curious if that's something that someone is looking into, or something that there is work being done to try to be able to predict on that end, which could also help on the further end that you're mentioning.
Thank you. So that's not something in particular that we're working on today, but I believe actually NVIDIA and Jensen Huang have a massive digital twin of the Earth initiative that I think is working on some of those problems.
Yeah, actually there is quite a lot of work being done in creating realistic models of weather patterns. We did a TV program on it. It's a very difficult problem to solve, but you can imagine the potential if you can predict there's going to be a very windy day to make sure that we switch mostly to wind for that particular day. So that is the plan for the future, but that's a really good question.
Yeah, for sure.
Micheline, thank you so much for joining us. Ladies and gentlemen, Micheline Casey.
Thank you.